Let's ultrasound. On today's edition of Doppler Ultrasound, we're covering Doppler 101, the basics. So let's start with what is Doppler ultrasound? Doppler ultrasound lets us assess blood flow characteristics. And it involves comparing the frequency that's transmitted into the tissues, we call this the transmitted frequency, to the frequency that's received back to the transducer, and this is known as the received frequency. The transmitted frequency goes into the tissue and encounters a moving object, which in this case is going to be RBCs, which are red blood cells. And the frequency that is reflected back to the transducer, the receive frequency, is dependent upon which direction the object or the red blood cells were moving. The transducer measures this shift in frequency between the transmitted and the received frequencies to determine the speed and the direction that the object was moving. And this is known as the Doppler shift. And this is the difference in frequency between the transmitted and the received frequencies. And a Doppler shift can be either positive or negative. And when there's a large difference between the transmitted and received frequencies, this is known as a large Doppler shift. And this represents high velocity flow. And when there's a small difference between the transmitted and received frequencies, this is a small Doppler shift, and this represents low velocity flow. A Doppler shift can be either positive or negative. With a positive Doppler shift, the object, such as the red blood cells, are moving towards the transducer, and the frequency that's reflected back to the transducer, this is the received frequency, is higher than the original frequency that was sent out, which is the transmitted frequency. And this results in a positive Doppler shift, and this represents blood flow that's above the baseline. With a negative Doppler shift, the object or the red blood cells are moving away from the transducer, and the frequency that's reflecting back to the transducer, this is the receive frequency, is lower than the original frequency that was sent out, the transmitted frequency. This results in a negative Doppler shift, and this represents blood flow that's below the baseline on an ultrasound. There's 3 types of Doppler ultrasound: power Doppler, color Doppler, and spectral Doppler. First, let's talk about power Doppler. Power Doppler detects the presence or absence of blood flow, and it measures the strength of the Doppler signal that's returning to the transducer rather than a shift in frequency. And this has high sensitivity. It picks up small vessels and low flow velocities. However, it cannot detect the velocity or the direction of blood flow. Now, note that there's newer technology that's known as directional power Doppler, and this can detect direction of blood flow. However, with traditional power Doppler, it detects only the presence or absence of blood flow. Traditional power Doppler is oversensitive, and it's subject to what we call color flash artifact. However, a strength with power Doppler is that it's not dependent on angle or subject to aliasing. Flash or motion artifact are artifactual echoes within a power or color Doppler box due to motion, and that's demonstrated in the bottom image on this slide. The second type of Doppler is color Doppler, and this can detect the presence or absence of blood flow, a flow velocity range, and the direction of blood flow. The definition of flow in terms of our discussion today is blood flow, and this is the motion of the red blood cells. Color Doppler assigns a color to the different speeds and directions of the flow and measures the frequency shift between the transmitted and the received frequencies. And the shift in Doppler frequency is displayed as either a positive or a negative shift on a color Doppler map. A positive Doppler shift is flow above the baseline and represents flow moving towards the transducer, while a negative Doppler shift is flow below the baseline and represents flow moving away from the transducer. The next type of Doppler is spectral Doppler, and there's two types of spectral Doppler. You have PW, which is pulsed wave spectral Doppler, and CW, which is continuous wave spectral Doppler. First, let's explore pulsed wave spectral Doppler, and this is the primary type of Doppler that's used in ultrasound imaging. And this collects Doppler information from a small area, which is known as the sample gate, and demonstrates the flow characteristics from that small region. And the flow characteristics are the flow direction, velocity, the waveform pattern, and the presence or absence of flow. And these flow characteristics are displayed as a spectral tracing or waveform on the ultrasound image. And there's characteristic waveform patterns for arteries versus veins and for each vessel in the body. And any deviation from the expected waveform pattern can indicate the presence of disease or indicate incorrect machine settings. With pulsed wave spectral Doppler, there is a solitary ultrasound crystal which both sends and receives a signal. And the signal is intermittent. On, off, on, off. So you have sending time, plus you have listening time. And the crystal is going to have to wait to receive a signal back before it can transmit another pulse. Pulsed wave Doppler ultrasound can produce a grayscale ultrasound image, power Doppler, color Doppler, and spectral Doppler information. With increasing depth, the journey time increases. This is the round trip for the ultrasound sound waves. And the crystal is going to have to wait longer for the signal to return before another pulse can be sent out. Now let's talk about continuous wave spectral Doppler. With this type of spectral Doppler, you have two ultrasound crystals. One crystal sends a signal, and one crystal is receiving a signal. And the signal is always on. You don't have to wait for the echo to return to the transducer, as one crystal is always sending and one crystal is always receiving. And this type of ultrasound can provide a waveform data tracing on graph paper, and it can also produce an audible Doppler sound. This type of spectral Doppler cannot form a grayscale ultrasound image. Now let's move on to some color Doppler basics. With color Doppler, you have what's called a color map. And this is a color-coded map of the Doppler shifts. And this is located on the side of the ultrasound monitor when the color Doppler control is turned on. And on this color map, you have a baseline. And this is a black line on the color map that separates the positive Doppler shifts from the negative Doppler shifts. And this represents an area of zero flow or zero Doppler shift. And the baseline control on the ultrasound machine allows this baseline to be shifted higher or lower on the color map. And shifting this baseline changes whether more or less positive or negative Doppler shifts are displayed. So it emphasizes either flow towards or flow away from the transducer. And this can help avoid signal wraparound or aliasing. However, it's crucial to note that shifting this baseline does not change the velocity scale. So what do the colors on the color Doppler map signify? The color that's above the baseline represents a positive Doppler shift, and this is flow moving towards the transducer, and it's always going to be the color that's at the top of the color Doppler map. Next, we have the color below the baseline, and this represents a negative Doppler shift, and this is flow that's moving away from the transducer, and this is always going to be whatever color is at the bottom of the color Doppler map. And on the color Doppler map, black represents the baseline, and this separates the positive and the negative Doppler shifts, and this is an area of zero Doppler shift or zero flow. On a color Doppler map, brighter colors represent higher velocity flow, and darker colors represent lower velocity flow. And then mosaic colors represent mixed velocity flow. And this is aliasing due to either pathology, vessel dynamics, or artifact. Next, you have the Doppler box, and this is a box that populates onto the screen when either color or power Doppler is turned on. And the area inside the box displays the color Doppler signals, either positive or negative. And we also have the velocity scale. Colors are assigned on the color Doppler map to signify different velocities of flow. The further away from baseline in either direction, and baseline is the black color on the color Doppler map, the higher the velocity of the blood flow. And there's a number on each end of the color Doppler map, which represents the range of velocities that are displayed on the color map. And the range of displayed velocities can be changed with the PRF or the scale control on an ultrasound machine. Now let's look at this image. In this image, the yellow arrow depicts the direction of the ultrasound beam. On the color Doppler map, there's a red color above the baseline. So red in this instance represents flow moving towards the transducer or flow above the baseline. And this is the bottom vessel in the diagram. In this same image, you can see that blue color is below the baseline. In this particular instance, blue represents flow moving away from the transducer or flow below the baseline. And this is depicted in the top vessel in this diagram. Now let's look at a schematic showing what flow towards the transducer or flow towards the ultrasound beam will look like. In the diagram on the far left, the yellow arrow depicts the location of the transducer or their ultrasound beam. The flow direction is moving towards the yellow arrow, which is the ultrasound beam, and the color on the top of the color Doppler map is blue. So in this instance, blue represents a positive Doppler shift, and blue represents flow moving towards the transducer. In the middle image, the yellow arrow represents the location of the transducer or ultrasound beam. Red is the color on the top of the color Doppler map. So red is the color that represents flow moving towards the transducer. And you can see that that flow is traveling towards that yellow arrow or ultrasound beam. So the red color in this instance represents flow moving towards the transducer and a positive Doppler shift. In the image to the far right, red is the color at the top of the color Doppler map. So red is going to represent flow moving towards the transducer. And blue is the color at the bottom of the color Doppler map. So blue in this instance is going to represent flow moving away from the transducer. The yellow arrow in this diagram on the far right represents the location of the transducer or ultrasound beam. In this diagram, let's focus on the bottom vessel. The flow direction is moving towards the yellow arrow or ultrasound beam, and it's red in color, which matches the color at the top of the color Doppler map. So this represents a positive Doppler shift and flow moving towards the transducer. Now let's look at some schematics of flow away from the transducer or the ultrasound beam. In the image to the far left, the yellow arrow represents the location of the transducer or ultrasound beam, and flow direction is moving away from the yellow arrow or ultrasound beam. The color on the bottom of the color Doppler map is blue, so blue in this instance is going to represent a negative Doppler shift or flow moving away from the transducer. In the middle image, the yellow arrow depicts the location of the transducer or ultrasound beam. The flow direction is moving away from the yellow arrow or ultrasound beam. The color on the bottom of the color Doppler map is red. So in this instance, red is going to represent a negative Doppler shift or flow moving away from the transducer. On the image to the far right, the yellow arrow represents the location of the transducer or ultrasound beam. And we're looking at the top vessel in this instance. Blue is the color on the bottom of the color Doppler map. So in this instance, blue is going to represent a negative Doppler shift and flow moving away from the transducer, which is depicted in the top vessel in this diagram to the far right. When using color Doppler, there's also a control known as the color invert control. And this control flips the colors assigned to the positive and the negative Doppler shifts on the color map. It does not change the direction of flow, however. Note that a color Doppler map is always going to display positive Doppler shifts at the top of the color map, above the baseline, and always display negative Doppler shifts at the bottom of the color map or below the baseline. So it's really crucial to pay attention to what color is on top. And note that red is not always on the top and blue is not always on the bottom. So it's crucial to look at the map every single time that you turn color Doppler on. Here's two scenarios demonstrating the color invert control. On the far left image, red is the top of the color map. And so red in this image is going to represent flow moving towards the transducer, or the yellow arrow in this depiction. And in this far left image, blue is the bottom color on the color Doppler map, and it's going to represent flow moving away from the transducer or away from that yellow arrow. Now, in the image on the far right, the color invert control has been applied. The flow is still moving in the same direction as it was, however, the color assigned to that flow has changed. So blue now represents flow moving towards the transducer, and red, which is at the bottom of the color map now represents flow moving away from the transducer. Now let's explore some color Doppler pitfalls, and most of these are related to color Doppler artifacts. And the first one is known as noise, and these are artifactual color echoes within a color or a power Doppler box that do not correspond to actual blood flow signals. And it appears as pixelated dots of color, which are sometimes grouped together to form lines or shapes within a color or power Doppler box. And this is due to the color or power Doppler gain being set too high. The color Doppler gain is a control on an ultrasound machine that amplifies or decreases the Doppler shift signal. So commonly when we think of gain, we think of the grayscale control, and the grayscale gain control either brightens or darkens the entire ultrasound image by amplifying or decreasing the signals that have already returned to the transducer. And color Doppler gain works in a similar fashion. When this color Doppler gain is set too high, you're going to get spurious echoes or noise present within the color or power Doppler box. And when the color Doppler gain control is set too low, you're going to have decreased color or power Doppler sensitivity, and blood flow information can be lost. To set the correct color or power Doppler gain level, you want to turn the color Doppler gain control all the way up until noise is displayed within the color or power Doppler box. And then you want to turn the gain control slowly down just until the noise disappears. And this is the optimal color or power Doppler gain setting, which is sensitive enough to pick up flow, but low enough to avoid noise artifact. The next artifact is known as color bleed, and this is when the color or power Doppler gain is set too high and the signal spills over the edge of a vessel. And artifactual color echoes or noise are displayed in areas where there should be no color echoes. And this makes vessels appear wider than they truly are and obscures vessel walls. The color or power Doppler gain should be set so that the walls of the vessel are clearly visible and no Doppler signal is spilling outside of the vessel walls. The next artifact that can occur is aliasing, and this is inaccurate flow and velocity signals due to vessel dynamics, machine limitations, or improper Doppler settings. And this appears as Doppler signals that are displaying the wrong direction or velocity information, which is multicolored Doppler signals on color Doppler, or a wraparound of waveform peaks on a spectral Doppler waveform. Artifactual flow velocities occur when the velocity of the flow has exceeded the Nyquist limit. Causes of aliasing are vessel narrowing, such as stenosis, branching or curvature, increasing Doppler angles, which are angles above 60 degrees when using Doppler, high velocity flow, this is flow above the Nyquist limit, and or a PRF or scale control, which is set too low. It's crucial when talking about aliasing to also talk about the Nyquist limit and pulse repetition frequency. First, let's explore the Nyquist limit. Doppler has a limit, and past this limit, an ultrasound machine can no longer measure the velocity of the flow because it's too high. The maximum limit of the Doppler shift that can be measured and displayed by an ultrasound machine is known as the Nyquist limit, and the Nyquist limit is half of the PRF. Above the Nyquist limit, aliasing occurs. If the range of displayed velocities is set too low, then aliasing occurs. Now let's talk about the PRF, or pulse repetition frequency. ultrasound pulses are transmitted at a certain frequency, and the number of pulses of sound that occur in 1 second is known as the PRF, or pulse repetition frequency. On an ultrasound machine, there's an ultrasound control known as the PRF, or the scale control. And the PRF, or scale control, changes the range of velocities displayed on the color Doppler map or the spectral Doppler waveform tracing. And this is a control that can be used to help eliminate aliasing. Now let's dive into some spectral Doppler basics. With spectral Doppler, there's a spectral waveform, and this is a waveform tracing that represents the pattern of blood flow present within the spectral Doppler sample volume or window. There's also a velocity scale, and this is a bar on the side of the waveform tracing that shows the velocity of flow in centimeters per second. And this is the range of velocities that the scale, or PRF control, is set to pick up, and it can be increased or decreased for higher or lower velocity flow. There's also a sample volume or sample gate, and this is a small Doppler gate placed within an area to be sampled, and flow information from within the sample volume or gate is recorded in the form of a waveform tracing. Now, it's also crucial to define anterograde flow and retrograde flow. Anterograde flow is flow moving in the expected direction for a vessel, and retrograde flow is flow that's moving in the opposite direction than is expected for that vessel. Note that these are not necessarily tied to positive or negative Doppler shifts. When using spectral Doppler, the baseline is the horizontal line in the middle of the spectral waveform tracing. And this represents an area of zero flow, or no Doppler shift. And it separates the positive from the negative Doppler shifts. And this baseline can be moved up or down to accommodate higher or lower velocity flow. Moving the baseline does not change the velocity range itself. Rather, it changes whether a higher number of positive or negative Doppler shifts are displayed on the waveform, which can help eliminate wraparound of the waveform tracing. A waveform pattern above the baseline generally represents flow moving towards the transducer, or a positive Doppler shift, and a waveform pattern below the baseline typically represents flow moving away from the transducer, or a negative Doppler shift. However, it's crucial to know that this can be inverted with the invert key, meaning that the positive and negative shifts will be switched. This differs from color Doppler. With color Doppler, positive Doppler shifts are always above the baseline, and negative Doppler shifts are always below the baseline, although the colors can be inverted. But with spectral Doppler, the actual positive versus negative Doppler shifts themselves can be flipped. With spectral Doppler, arteries tend to be above the baseline and veins below the baseline, though not always, and a representative vessel that doesn't follow the rules is the portal vein. Portal vein flow, even though it's venous flow, it moves into the liver, so the flow is above the baseline and a positive Doppler shift, even though it's venous flow. And also a thing to note is that some vessels have flow that is both above and below the baseline. When using spectral Doppler ultrasound, there is a control known as the spectral Doppler invert. And pressing this key inverts the positive and the negative Doppler shifts. And it flips the velocity scale on the spectral waveform tracing to display negative Doppler shifts above the baseline and positive Doppler shifts below the baseline. And this is opposite what happens with color Doppler. When the invert key is pressed with color Doppler, the positive and negative Doppler shifts stay in the same locations, and only the color changes. With spectral Doppler, the positive and negative Doppler shifts actually change positions. To determine which side of the baseline is displaying a positive versus a negative Doppler shift, you want to look at the velocity scale numbers. Negative numbers are going to represent negative Doppler shifts and flow away from the transducer, and positive numbers on that scale will represent positive Doppler shifts and flow moving towards the transducer. And these numbers can be viewed on the velocity scale, which is to the side of the spectral Doppler waveform tracing. Let's talk angles. Doppler angles are crucial to obtaining accurate Doppler velocity information. And the Doppler angle is the angle from which the spectral Doppler sample is obtained. An angle of 0 degrees is ideal, but usually not attainable. Angles from 0 to 60 degrees provide accurate Doppler shift information, and angles above 60 degrees, these are the 61 to 89 degree angles, provide errors in velocity, and they either over or underestimate flow velocities. The larger the angle, the greater the error. An angle of 90 degrees will provide no Doppler shift information because no Doppler shift occurs when the transducer and the vessel are perpendicular to each other. And it's crucial to align the angle in the center of the vessel within the direction of flow. Now let's cover a few spectral Doppler waveform basics. First, let's talk arteries. An artery carries oxygenated blood from the heart to the rest of the body, and a normal artery is going to have pulsatile flow, and this is flow that accelerates and decelerates in response to cardiac contraction. And you can actually visualize an artery pulsating on the ultrasound image. Arterial walls are going to be firm, echogenic, non-compressible, and arteries are going to have 3 basic flow patterns dependent upon their location in the body and the structures that they supply. And that's going to be triphasic, biphasic, or monophasic. Arterial flow is generally going to be above the baseline, and an arterial waveform is going to be divided into phases, which are tied to the contraction and the relaxation phases of the heart, which are systole and diastole. And arterial flow is either going to be high resistant flow or low resistant flow. Now let's look at a basic arterial spectral Doppler waveform. And this is a triphasic pattern. Flow above the baseline is going to be flow towards the transducer, as long as the spectral Doppler invert key is not on. And flow below the baseline is going to be flow away from the transducer. The waveform is going to be split into 2 different halves. The first half of the waveform represents what's happening during systole, and the second half of the waveform represents what's happening during diastole. The waveform starts with a sharp upstroke, which culminates at peak systole. This is the top of the waveform. And then it moves down a bit into the dichrotic notch. And this dichrotic notch is a notch on the waveform that indicates the end of systole and the start of diastole. And then the waveform is going to continue down, and it's going to go below the baseline and show an element of reverse flow in early diastole. And then it's going to rise back up above the baseline and show forward flow in end diastole. There's also a spectral window, and this area should be clear of echoes. When it's filled in with echoes, this indicates turbulence within the waveform. A crucial piece to interpreting a spectral Doppler waveform is understanding the direction of flow. To determine this, you want to look at the spectral waveform, and there's going to be a velocity scale on the side of the waveform, and the velocity scale is going to have pluses and minus signs, and these represent positive versus negative Doppler shifts. If the waveform is on the side of the baseline that has positive numbers, then the waveform represents flow moving towards the transducer and a positive Doppler shift. And this could either be located above or below the baseline, dependent upon whether or not the invert key is on. If the waveform is on the side of the baseline that has negative numbers, then the waveform represents flow moving away from the transducer and a negative Doppler shift. And the invert key is going to flip the positive and the negative signs either above or below the baseline. So it's crucial to compare the waveform direction of flow with the color Doppler map and vessel information to understand the true direction of flow within a vessel. Moving along with spectral Doppler basics, the next thing to talk about is velocity, and this is the rate of blood flow, and it's based on the speed and the direction of the flow, and it can be measured at peak systole, which is the highest velocity within the waveform, or it can be measured at end diastole, which is the lowest diastolic value within the waveform, and or it can be measured as a mean value, which is a velocity average over the entire waveform. And velocity is going to be related to volume, pressure, and vessel diameter. Velocities in the arteries are highest during systole and lowest during diastole. And velocity is fastest in the middle of a vessel and slower near the vessel walls. Velocity is visualized as darker or lighter colors on a color Doppler map, or as increasing numbers in either a positive or a negative direction on a spectral Doppler velocity scale. And that velocity scale is going to be found right next to the waveform tracing on spectral Doppler ultrasound. Another crucial factor to understand when interpreting arterial spectral Doppler waveforms is resistance. And resistance are factors that impede or slow blood flow. It's the resistance that the blood experiences as it travels through the vessels. And arteries can change their resistance level to divert flow towards areas in the body that need it most. And on spectral Doppler waveform patterns, arteries will display either high resistance or low resistance patterns of flow, or mixed resistance patterns of flow. A high resistance flow pattern is a more pulsatile flow pattern that is found in extremity arteries and in areas of the body that do not need constant blood flow traveling to them. A high resistance flow pattern will either have little diastolic flow, no diastolic flow, or an area of flow reversal in diastole. Low resistance flow is for organs that need continuous flow going to them, such as the brain, kidneys, ovaries, testicles, etc. And these are arteries such as the renal, internal carotid, ovarian, and testicular arteries. And these all display low resistance patterns of flow. And low resistance flow is flow that is sustained throughout both systole and diastole. And a low resistance pattern is going to have an increased amount of diastolic flow. Another thing that spectral Doppler can look at is something called the resistive index. And this measures the amount of resistance, either high or low, that is present within a vessel. And this is commonly used in types of ultrasound that assess whether a vessel is losing its low resistance pattern. And loss of a low resistance pattern is an indication of declining organ function for an organ that depends on constant blood flow going to it. And this is commonly performed for the intrarenal arteries. Peak systole and end diastole are measured on the spectral Doppler waveform, and the ultrasound machine calculates out a number that shows whether an area is displaying continuous flow or low resistance flow, or if it's losing its low resistance pattern. And the resistive index scale is as follows. 0 is continuous flow to an area, which is low resistance flow. 1 is systolic flow to an area but no diastolic flow, and greater than 1 is reverse diastolic flow. Another thing to consider when looking at spectral Doppler waveforms is pulsatility. And pulsatility is blood moving through vessels at a variable velocity dependent upon the beat of the heart. And this is a rhythmic beat or pulsation. And the flow velocity is going to accelerate and decelerate as a result of cardiac contractions. And this is a normal blood flow pattern for arteries. And it looks at the maximum systolic, the minimum diastolic, and the mean velocity magnitudes. And as diastolic flow increases, pulsatility decreases. So when looking at waveforms, arterial waveform with a high pulsatility pattern is going to have little to no diastolic flow. It's going to have steep slopes, higher velocity flow, and sharper systolic peaks. While an arterial waveform with a low pulsatility pattern is going to have higher diastolic flow, shallower slopes, lower velocity flow, and broad systolic peaks. It's important also to consider that veins can have a pulsatile pattern in some situations. Normal veins are going to be phasic, meaning that the flow is going to accelerate and decelerate in response to respiration, which means they're going to have more of a rounded waveform. However, veins located near the heart are going to display a pulsatile pattern due to their proximity to the heart, and this means they're going to have a more pointed waveform appearance. With veins, higher pulsatility means sharper, pointed peaks on the waveform, and a lower pulsatility pattern or a more phasic venous pattern is going to have rounded peaks. Another thing that can be calculated when looking at spectral Doppler arterial waveforms is the pulsatility index, or PI. This assesses the pulsatility in an artery by measuring the maximum, minimum, and mean velocities. And it's another method of evaluating resistance in a vascular system that's pulsatile. And it takes the entire waveform into account, rather than just the maximum and minimum values that are used to calculate the RI. And the pulsatility index decreases with distance from the heart. And we commonly use this in OB to evaluate the umbilical, uterine, and fetal circulations. And as diastolic flow increases, the pulsatility is going to increase. A lower PI calculation is going to be a higher pulsatility waveform, and a higher PI calculation is going to be a lower pulsatility waveform. Now let's talk about a typical venous waveform when using spectral Doppler. Veins are blood vessels that carry deoxygenated blood from the body back to the heart. And on ultrasound, there's 5 characteristics of normal venous flow. The flow should be spontaneous, occurring by itself. It should be non-pulsatile, meaning it's got a rounded waveform rather than sharp peaks, unless the vein is located near the heart, in which case it will have a pulsatile pattern. The flow should be phasic, which means that it accelerates and decelerates in response to respiration, and this gives it its characteristic rounded waveform shape. It's also going to be augmentable, meaning that if you squeeze an area below the area of interrogation, you'll get a rush of blood flow that displays on the waveform tracing. And veins are also thin-walled and compressible on an ultrasound with transducer pressure. A venous waveform is typically going to be phasic, which means that it accelerates and decelerates in response to respiration, and it's generally going to be below the baseline and generally going to be flow away from the transducer, though not always. Note that the portal vein is venous flow, however, portal vein flow travels into the liver, which is flow moving towards the transducer and a positive Doppler shift. Another thing to understand when performing studies that have Doppler is the terms duplex versus triplex ultrasound imaging. And that's because ordering doctors sometimes refer to studies that involve spectral Doppler as duplex studies. Duplex or triplex ultrasound imaging means that you're using more than one type of ultrasound at the same time. Duplex imaging means that you have a grayscale ultrasound image plus either spectral Doppler, color Doppler, or power Doppler. So you're using 2 types of ultrasound at once. And duplex is a term that means 2. Triplex imaging is a term that means 3. For this, you have a grayscale ultrasound image, plus you're either using either power or color Doppler imaging, plus you're also using spectral Doppler at the same time. And typically, when vessels are being interrogated, we're actually using triplex imaging because we almost always use color Doppler and spectral Doppler in conjunction with one another. However, ordering doctors often order this as a duplex ultrasound study. But what they're really asking for is a typical spectral Doppler, color Doppler, and grayscale ultrasound interrogation of an area of interest.